Hello everyone, and this is Devabrata. Welcome to all to our channel Schrodinger's Cat. And in our previous lecture, we just discussed the particle physics in the topic of nuclear and particle physics, and today we will discuss the topic LS and JJ coupling from the topics the atomic and molecular physics. And basically in the today's class in IIT JAM, only in atomic physics 2 or 3 questions are come, and the JEST exam 2 and the TIFR 1 or 2 and the CSIR NET 3 or 4 and the GATE 5 or 6 questions are coming here. And almost from the LS and JJ coupling, basically 1 or 2 questions are come from this topic. And today we will cover the energy correction, LS coupling scheme and spectroscopic terms of non-equivalent electrons, spectroscopic terms for the equivalent electrons, the Hans rule, selection rule in LS coupling, JJ coupling scheme and spectroscopic term. So let's get started. Basically, I just say one thing. Today, for the exam point of view, we just summarize the chapter in a nutshell, and after we get the time, we just cover all the topics elaborately. So we just summarize the chapter and go through the problems in coming in the CSIR NET and GATE exam. So first of all is the LS and JJ coupling. The first one is the energy correction. The energy correction, and one thing is that for Z less than 30, the LS coupling occurs, and for Z atomic number greater than 30, JJ coupling occurs. And the energy correction, first one is the kinetic energy. So basically for the kinetic energy, this correction will becomes L1 to N Pi square by 2m. Second one, electrostatic interaction energy. Electrostatic interaction energy. So basically it is summation I1 to N Jd square by Ri, and the mutual electrostatic energy, that summation I1 to N summation over J 1 to N minus 1 Jd square by Rij. This is the mutual electrostatic energy. And the residual electrostatic interactions, and here one thing is that spin and the spin orbit, these are the points for the energy correction. And the number of energy level, is 2s plus 1. And second one is the LS coupling scheme and spectroscopic term. So spin correlation effect. First one, the LS coupling scheme. LS coupling scheme. So for this scheme, that spin correlation effect, spin goes up and energy goes down. So basically for spin 1 half and spin 2 half, so the multiplicity 2s plus 1 multiplicity and s goes to mod s1 minus s2 to mod s1 plus s2, and this is the total spin angular momentum. And second one is the residual electrostatic interaction. This is the spin effect, and second one is the residual electrostatic interaction. So for residual electrostatic interaction, here the L and this follow, and the orbital angular momentum L 1, 2, 3 for P, D and F, and L varies from mod L1 minus L2 to mod L1 plus L2, the total orbital angular momentum. And third one is spin orbit interaction. This is the spin orbit, this is the spin, and this is the for spin orbit interaction, the total angular momentum and the E and the total J is equal to L plus S, where the J value should be L minus S to L plus S, so L minus S plus 1, and this is basically 2s plus 1 for L greater than S and 2L plus 1 for L less than S. And third one is the spectroscopic terms, that the spectroscopic terms, basically first one for the non-equivalent electron. So atom with one optical electron 1s, this is for the non-equivalent. So basically the atom with one optical electron 1s, 2s half, the term symbol is 2s plus 1 multiplicity Lj. This is the term symbol, and the atom with two or more non-equivalent optical electron, suppose here given 4p 4d, for S1 half, S2 half gives S0 1, L1 1, L2 2, L1 2 3. Next one is S1 L1, that J 0 1 2, S1 L2 J 1 2 3, S1 L3, that total angular momentum 2 3 4. So 3p has CP2, CP1, CP0, these combinations. And second one is that term of two non-equivalent electron. For two non-equivalent electron, that the SS for 1s0 3s1, SP 1p1 3p1 2 3, SD for 1 d2 3d1 2 3. This is the term symbols. And for the term for 3 non-equivalent electron, this is for the 2 case, and for C non-equivalent electrons, basically such an example that 3d 4s 4p, here the S1 value half, S2 value half, S3 value also half. So S is equal to half C by 2, basically 2 doublet and quadruplet. And for L1 2, L2 0, L3 1, this gives L1 2 3. This is the P, D and F state. Suppose 2p term symbol written in the form half 3 by 2. This means 2 multiplet. Next one is that the spectroscopic term for equivalent electrons. For equivalent electrons, the spectroscopic term, so first one, a closed cell. First one, a closed cell. For closed cell like S2, P6, D10, full filled F14, this is written as 1s0, term always form. Second one, suppose P1 is equivalent to P5, P2 P4, D1 D9, D2 D8, same energy level, D3 D7, D4 D6. And second one, the P square P4, this can be determined, this is a equivalent energy and this is determined by the base scheme. Basically it says that if the ML1 is equal to ML2, then ms1 not equal to ms2, and ml should be ml1 plus ml2, and this base scheme is basically a elemental form like ml1 dot basically ml2, and this is written as ml and ml. This is by scheme here. And for the equivalent electron, that if J1 is equal to J2, so J value will become 2J minus 1, 2J minus 3 dot dot, and for J1 is not equal to J2, it lie between J1 minus J2 to J1 plus J2. The J value are lying in between this. And the third one is the spectral terms of equivalent electrons. Next thing is that the spectral terms of equivalent electron. So basically, electron configuration, and here the terms. So for electron configuration S1, and this is for S2, P6, D10, P1, P5, P2, P4, P3, D1, D9, last one D2, D8. The spectral terms is written as in the form of, for S1 2s half, for S2 P6 D10 1s0, for P1 P5 2p half C by 2, for P2 P4 1s0 1d2 CP012, for P3 2p half C by 2 2d C by 2 5 by 2 and 4s 3 by 2, and for D1 and D9 the two would happen 2d C by 2 5 by 2, and for D2 and D8 these combinations 1s0 1d2 1g4 CP 012 and CF 2 3 4. And last thing is the some selection rules. So for the order rules, order of term, that Hans rule is given that Vs plus 1 and energy down, L down, and the normal order means that less than half filled subcell, less than half filled subcell, so J and E, and for inverted order greater than half filled subcell, and for J up, energy down. And second one is the selection rule for LS coupling. LS coupling selection rules. So for one electron system, one electron atom, del L is equal to plus minus 1, del Ms is equal to 0. One electron atom without spin, del Ml is equal to 0 plus minus 1, del J equal to 0 plus minus 1, but J equal to 0, this J equal to 0, and last one del Mj 0 plus minus 1. And second one is the 2 electron transition. 2 electron transitions, that del L1 is equal to plus minus 1 and del L2 is equal to plus minus 2. This is for the 2 electron transitions. And the another one is the for many electron atom. Many electron atoms, that del L equal to 0 plus minus 1, but L 0 to 0 is forbidden, and del Ml is equal to 0 plus minus 1, del J 0 plus minus 1, but J value 0 to 0 forbidden transitions, del Mj 0 plus minus 1, and last one del S is equal to 0. This is the many electron atom selection rule for the transitions. And the last one is that basically the Laporte rule. For the transitions, it basically saying that the parity sum over L is even or odd of the electron configuration must change in an electric dipole transition. Basically odd, even. And another one, that JJ coupling scheme and spectroscopic term. We just complete LS coupling, and now JJ coupling scheme and spectroscopic term. So basically orbit spin gator orbit or spin orbit coupling. This is the order of the transitions, and first one is the spin orbit interactions, that spin orbit interaction, basically J L minus half and L plus half, and this one is the lowest energy. And for the residual interaction, that J value is equal to root over J into J plus 1 H cross, where J equal to J1 plus J2 to J1 minus J2. And basically one thing is that unperturbed level is equal to spin orbit energy plus electrostatic and spin energy. Electrostatic and spin energy. And the selection rule applied here, that for electrons del J equal to 0 plus minus 1, and for atoms del J equal to 0 plus minus 1, but J value 0 is forbidden. This is for the forbidden transition. This is the symbol. So we just summarize this whole topic of LS and JJ coupling by the formula. Now go ahead over the problem discussion session. So first problem is coming in CSIR NET December 2016. It says that in a LS coupling scheme, the terms arising from two non-equivalent p electrons are what? So basically for doing this you have to memorize the spectroscopic term. So for PP configurations, and I think you just try yourself and after just look upon these solutions. The S1 is half and the S2 half. So S is 0 1, L1 1, L2 1, so L value 0 1 2. Thus that S we just write in the formula section S0 L0, J would be 0, this term 1S0 or 1S, S0 L1, that J1, that terms would become 1P1 or 1P. S now S0 L2, J value 2, 1D2 or in short 1D. Now S1 L0, J1, CS1 or 3S. Next one S1 L1, that J0 1 2. You just find the J value and J L plus S, that CP C multiplet 0 1 2 or in short 3p. Last one, the S1 and the L2, so J value 1, 2, 3 and E2 3D 1, 2, 3 or 3D. So finally that our result, that 1s, 3s, 1p, 1d, 3d. So basically D would be our correct answer. Next one, coming in CSIR NET 2016 June, is saying that the ground state electronic configuration of titanium is this argon 3d2 4s2, which state in the standard spectroscopic notation is not possible in this configuration, is not possible. This is keep in mind. So basically the spectroscopic term for D2 are obtained, we just write here that the spectroscopic term for D2 are obtained that L1 2, L2 2, that L value 4, 3, 2, 1, 0, S1 half, S2 half, so S value 0, 1, 2s plus 1. Now the S0 L4, so J4, so combination 1G4, S0 L2, that become J2, gives 1D2, S0 L should 0, J should be 0, spectroscopic term 1s0, S1 L3, J would be 4, 3, 2, the spectroscopic term would be 3f 4, 3f 3, 3f 2, the S1 L1, J would be 2, 1, 0, and the spectroscopic term 3p2, 3p1 and the 3p0. So you just saying that, so 1s0 is here, 1d2 is here, 3p0 is here, so 1f3 is not, this is not the possible 1f3, so A would be our correct answers. Next one, coming in December 2015, is saying that the LS configuration of ground state of magnesium, aluminum and chlorine argon are respectively what? Ground state. So you just electronic configurations of this. So first of one, for the magnesium, the configuration is 1s2, 2s2, 2p6, cs2. So ground state 1s0. I just write in the chapter summary sections. 13 aluminum, the electron configuration 1s2, 2s2, 2p6, cs2, 3p1, and this is the 2p half, 2p 3 by 2, and since it's less than half filled, since it's less than half filled, so from the Hund's rule the ground state should be 2p half. And for the chlorine, 17 chlorine, 1s2 2s2 2p6 cs2 cp5, so 2p half 2p 3 by 2, and it is, since it's more than half filled, so ground state would be 2p 3 by 2. Next one is for the argon. The electron configuration 1s2 2s2 2p6 cs2 cp6, so ground state should be 1s0. So I think C 1s0 2p half 2p 3 by 2 and 1s0, so C would be our correct answer. Next one, coming in GATE 2019, the ground state electronic configurations of the rare earth ion Nd3 plus is Pd 4f3 5s2 5x 5p6, assuming Ls coupling. The Lendizzi factor of the ion is 8 by 11. The effective magnetic moment in unit of Bohr magneton mu b is what? You have to find the magnetic moment mu. So for 4f3, these configurations, for 4f3, that ml value should be what? This 1 2 3 4 5 6 1 2 3 4 5 6 7, so this is -3 -2 -1 0 +1 +2 +3, this is filled. So here L is 6, L6, S 3 by 2 and the J 9 by 2. So we have the formula mu Bj mu b root over j into j plus 1. So put this value, this is 8 by 11 mu b and spin 9 by 2 plus 1. So 8 by 11 mu b root over 9 by 2 into 11 by 2 Bohr magneton, and this is 3.62 Bohr magneton. So this is coming GATE net type questions, numerical answer type. So you have to write the 3.62 would be a correct answers. Next one, coming in GATE 2018, is saying that 4 mega electron volt gamma ray emitted by the de-excitation of F19 are attributed, assuming spherical symmetry, to the transitions of protons from 1d 3 by 2 state to 1d 5 by 2 state. If the contribution of spin orbit term to the total energy is written as CL dot S expectation, this is basically the CL dot S energy average. Here is written L dot S in terms of average value. The magnitude of C is mega electron volt is what? This is also the net type questions coming in GATE, 2 marks. So basically, formally here written the L1 and S half and the J1 is 3 by 2, J2 is equal to 5 by 2. So J should be L plus S, and the J square L square S square plus 2 L dot S, or L dot S is equal to J square plus L square minus S square by 2. So L dot S, this put this value, that J plus 1 minus L plus 1 minus S plus 1 H cos square by 2. So the energy alpha, that L dot S of spin 5 by 2 transitions state to L dot S 3 by 2. This is given in the questions. So 1D 3 by 2 state from 1D 5 by 2. So just put this value here, alpha 5 by 2 7 by 2 minus 3 by 2 5 by 2, and the constant h cos square by 2. Basically alpha, this value after 20 by 8 h cos square, and 20 by 8, basically this is the C, and daily is equal to 20 by 8 C. This is given 4 mega electron volt in the questions, 4 MeV. So you have to find this C value, each 32 by 20 mega electron volt is equal to 1.6 mega electron volt. So 1.6 would be our correct answers. C value 1.6. And I think we have already discussed the 5 questions coming in CSIR NET and GATE, and for your better conception and understanding, I just give the homework for the same problem. After doing this 5 plus 5 10 problems, I think you just do all the problems coming in these chapters, LS and JJ coupling. So basically for your homework, you just pause this video and take a screenshot. I just wait you for the 10 seconds. First question is coming from the CSIR NET, first 3 and second 2 is coming from the GATE. You just pause this video and take a screenshot. So finally we just covered 10 questions from the LS and JJ coupling. I think after doing all the questions, you should solve all the problems coming from the LS and JJ coupling and the topic atomic and molecular physics, and you should not leave any topic and any chapter from the CSIR NET. Basically in the next exam, the questions are coming from the unimportant topic also. It is very mandatory that you just do the important topic, and in the questions that you've seen that in the important topic the questions are most harder and the low important topics are the easy questions. So basically you should not leave all the topics. So basically you just focus the important and unimportant also. Basically I think after this you just can go through all the problems, finally solve this homework, and if anyone needs this file or the study material of my YouTube lecture, just mail without no hesitation catschrodingers1935@gmail.com. Last but not the least, thank you very much. Stay happy and well. Have a good day.